Okay, so this is a walkthrough of problem 99 about the speeder and the patrol car. This is like a standard chase problem with one little adjustment that the patrol car reaches a maximum speed. So it does not continually accelerate forever. It reaches a max speed. So what happens is there's a starting position. This would be t equals 0. And there's the speeder, and the speeder, passes this point, and the speeder is moving at some speed, right? We'll call it Vs, speed of the speeder. All right, and it just keeps moving at that same speed until it, gets to the part till the police officer reaches it. So it just keeps going all the way over till it gets to that speed. The police officer sees it, and as soon as it moves, it starts accelerating. And so this would be at t0, it does the same thing. It starts and it has some acceleration. We could call it AP if we want to, but there's no other accelerations. So it accelerates, and it accelerates until it reaches a max speed. We don't know when that is, but it's at some time, right? And so we could call that time, I don't know, we could call it, I'm going to call it TA, the acceleration time. I mean, you could call it T1, T2, T0. I mean, you could give it different names, but it's the time that it's accelerating. And then it reaches a max speed. We call it T max, the time to the max speed. And then it moves on at a constant speed until it gets to the same position as the speeder is, okay? So we could call this time here, I'm going to call that just time t, or we could call it t total if we want to, tt, right? So the time from 0 to TA is TA, whereas the time from TA to TT, this interval of time here would be time TT minus time TA, that interval of time. And so the question is, what distance do things go while they're doing that? Well, the speeder is moving at a constant speed. So delta X of the speeder is just going to be Vs T T, because it's just moving at a constant speed the whole time. Now, while the police officer is accelerating, we're going to have delta X, the delta X of the police car while it's accelerating. I'll call it delta X A. I could call it delta X PA, but when you start having a lot of subscripts, it starts getting a little cluttery. So I'm just going to call it delta X A, and that is going to be 1/2 A TA squared. And then eventually it's going to hit that max speed. So I'm going to call that, and that distance, I'm going to call that delta X, delta XM for the max, when it's at its max speed. So delta XM, that's going to equal VM, its max speed, times the time of that interval from TA to TT. So that's TT minus TA, right? That's that time interval, okay? And the first question here is asking us, how long does it take the patrol car to catch the speeder? How long to catch the speeder? So what we're looking for is that total time, right? We're trying to find this total time. And when the times match up, the total distance is going to match up, right? So what we could say is delta x of the speeder, the distance the speeder goes, will equal the distance the police car traveled while it was accelerating plus the distance it traveled while it was at its max speed. And that would be, that gives us this general relationship here of Vs Tt equals 1/2 A TA squared plus Vm Tt minus TA. And we're trying to solve for TT. Now, the only issue here is we don't know what TA is. We don't know the time of the acceleration. So we need a second equation of some kind to figure that out. And there's many different ways, but I think the easiest and obvious one would be to just use the definition of acceleration. A equals delta V over T. And what T are we talking about here? We're talking about that accelerating time. So we can say that TA equals delta V over A, and delta V is V final minus V initial. Well, V final is that V max, that final speed, and V initial was 0. It started from rest, so it's just Vm over A. You always got to be careful here when you do these delta V calculations, because sometimes the initial speed is not 0, but in this case it is. So the time is just the speed or the velocity over the acceleration, though that is not always the case. You got to really make sure that you know the intervals you're referring to. But here we've got a second equation, so now we can plug that in for TA, and that brings us down to a single variable equation. So that is Vs Tt equals 1/2 A times TA squared, that's Vm over A squared, plus Vm times Tt minus Vm over A. And now this is a single variable equation, and you should be able to go ahead and calculate TT, and then that should be enough to carry you through the rest of the problem. One thing to keep in mind, these units are in kilometers per hour and kilometers per hour second for the velocity and the acceleration. You might think you need to convert these kilometers per hours into meters per second and kilometers per hour second into meters per second squared. You certainly can do that, but you do not have to, because this is kilometers per hour and kilometers per hour second. You can just work with these numbers when you do your evaluations finally, and it should work out because the kilometers are going to cancel kilometers, the hours will cancel hours, and you'll just be left with seconds. If you're not sure, just look it up, just fill in the values and keep the units there, and you'll see what units cancel. So it should work out. Okay, so I'm going to work through the actual solution here. So this is Vs Tt equals 1/2 A times Vm squared over A squared, and that's going to cancel one of those A's, plus Vm Tt minus Vm squared over A. And we want to solve for TT, so I'm going time total, so I'm going to move this value over. Vs Tt minus Vm TT equals 1/2 BM squared over A minus BM squared over A, right? So I moved this term over to the other side, and then I just have these two terms left on the right side. Now, if you notice here, we've got a VM squared over A and a VM squared over A. So 1/2 minus 1, that's going to be a negative. So I'm going to just go ahead and multiply everything by -1. Make that negative, positive, negative, positive, right? And then things will reduce to positive values. And this would be VM, the max speed of the police officer, minus VS, the speed of the speeder. The max speed of the police officer is 190 kilometers an hour, and the speeder is 125 kilometers an hour. So this will make everything positive if we do this. So I'm going to factor out the TT, and that gives us VM minus VS times TT equals, that would be VM squared over A, and that's 1 minus 1/2. So just 1/2, like that, which is just VM squared over 2A. And then we just divide out this VM minus VS. So T total equals VM squared over 2A times VM minus VS. And now we just have to evaluate. And again, you'll see that if we do this, we don't have to actually convert because we have kilometers per hour and kilometers per hour second. So Vmax is that 190. So 190 kilometers per hour squared over 2. A is 8 kilometers per, that's a kilometer per hour second, times 190 for Vmax minus 125. And those are kilometers per hour. So let's go ahead and I'm going to bring that up here. And that is 190 squared, kilometers squared per hour squared, over 2 times 8, that is 16. That is kilometers per hour second, times 190 minus 125 is 65 kilometers per hour. And if we look at this, we've got kilometers squared over kilometers times kilometers. So all those kilometers cancel. That's kilometers squared on the bottom, canceling kilometers squared on top. We've got an hours times an hour. That's an hour squared, right? Hours squared over hours squared. Those hours cancel. And that leaves us with just units of seconds. So we could have converted our kilometers per hour into meters per second, but it just wasn't necessary. So this is 190, that's squared. That's 19 times 10. And they're squared, they're both squared. Over 16. 16 is 2 to the 4th. And 65, that is 5 times 13. And that's seconds. And that's just going to be 19 squared. 10 is 2 times 5, so that's 2 squared times 5 squared over, that's 2 to the 4th times 5. put in little multiplication symbols here, times 13. And one of those 5s cancels and 2 of the 2s cancel, leaving us with, that's units of seconds, leaving us with 19 squared times 5 over 2 squared times 13 seconds. And you could have simplified that and get this, some exact answer. But if you go ahead and put it in your calculator and multiply it through, this comes out to be 34.711, something like that. So 34.711 seconds, even that's rounded actually, which is at significant digits, right? We've got 2 significant digits for our acceleration. So this is 35 seconds. So that's our time. So then we go on to the next part of the problem, which is to calculate how far does each car travel? Well, we know they travel the same distance, right? So might as well just use this, right? We could obviously add these 2 up and do it as well, but that's the easier choice. So delta x s equals vs times t t, and it would be great to actually, we could actually just say vs times this value, vs times, and then do the whole process again if you want to be really precise. But why don't we just just go ahead and use this value here, and we know that vs is going to be 125 kilometers per hour times 35 seconds. So here, or 30, maybe we should be a little more exact and say 34.711 seconds. And now here we do need to make a conversion. We do have to convert those hours to seconds. So I would just make seconds and hours here, and 3,600 seconds for 1 hour, and then seconds cancel like that, and hours cancel, and we're left with kilometers. Of course, we could also convert it into meters. All right, maybe we'll do that at the end, depending on the size of the value we get. Okay, so that's going to be 34.711 times 125 divided by 3,600. And that comes out to be delta XS equals 1.2053 kilometers, which we've got 2 significant digits. So that's delta XS approximately equal to 1.2 kilometers, or if you prefer, if you're uncomfortable, you can just say 1,200 meters. All right, so that's part B. And then part C is to sketch the position time graph for each car. Okay, so to do this, we would need to, make a graph. And maybe it would be good to know what this TA is for that. That's the thing that might be useful for the purposes of graphing here, to actually know what that TA is, right? And we could figure that out, right? We know that TA is the maximum was 190 kilometers per hour over A was 8 kilometers per hour second. So kilometers cancel, hours cancel. We're left with seconds. And we have 190 over 8, which is 23.75 seconds. Or about 24 seconds. So that's about what that time is. About 24 seconds. And remember, the total time we found out was about 35 seconds. So the second interval is about 11 seconds. Right, for a total time of about 35 seconds. Okay, so we could go ahead and make a graph to figure out what that is. All right, and to do that, we could go to some graphing software, or you can just graph it by hand, right? It goes from a parabolic to a linear graph. That's the thing you have to realize. But I'll go ahead and bring that up here. Okay, so now we're at some graphing software here. So we could make those two graphs. So the speed of the speeder, right, is going to be the 125, right? We have 125 kilometers per hour, and we would need to actually convert that into 25 kilometers per hour. So that would be 1,000 meters per 1 kilometer times 1 hour per 3,600 seconds. So there's the actual speed times, it's X here in this graph because that's this axis, but it's really T, right? This is the time. This is our variable, our independent variable. And we're going from 0 less than T or up to, I'm just going to go up to 40, up to the end of that time interval. But I think we realized that time is actually, it was 35 seconds, right? So if we wanted to, we could go here up to 35 seconds, something like that. That's where they actually meet. Doesn't say they actually stop. Probably time really keeps going, but that's the time we're curious about. Whereas the police officer, right, it had some acceleration. So the acceleration would be 1/2 times A, that was 8. Now that was kilometers per hour per second. So we need to convert that into, we do need to convert that into meters per second. So that would be, again, that 1,000 over 1 times that same 1 over 3,600, right? So that's, so this would be, this is kilometers per hour second. Now it is meters per hour second, and now it's meters per second squared. Yes. So that's one. So this would be x squared, like that. But we are only doing this from 0 less than t until basically it was the 24-second mark, I believe, that we went to. So something like that. That was the 24-second mark. And then the last bits of time, so that was the acceleration. That was until the 190 kilometer an hour speed. And then finally, it was going at its max speed. So that would be like this, except the speed that the police officer was 190. Okay. However, it didn't start that speed at 0. It started that speed after this time here. So I would shift that over 24 like that. And it was therefore, it was going to be ahead by a certain amount. So it's which is basically this value right here. So like 639, I'm going to say 600. Yeah, going to make it 638.934 plus 638, something like that. And it's moving at that between 24 less than X less than 35. All right. And there we go. We have all the motion graphed, right? The black line here, this is the speeder moving at that constant speed. And this is the police officer accelerating. This is while it's speeding up. And this is it driving at that max speed. And then they both meet up here at that 35-second mark at this position that's just a little bit above 1,200 meters, right? Just above the 1.2 kilometer mark, right? This is in meters, and these are in seconds. If we scale this a little differently, we could do it in kilometers and hours. So that would work just as well. All right. I hope that's a detailed explanation.